All right, so now that we're done with integration by parts, we're going to dive into trig integrals or trigonometric integrals. And this actually will be something we'll be doing for two sections. Here we're just integrating directly integrals for trig functions like sines and cosines. In the next sections, we'll be using what are called trig substitutions, where we may want to use trig functions to simplify the integrals that we're working on. So we're going to spend a lot of time with trigonometry basically over the next couple of classes. So now the techniques we'll be looking at here mainly fall into three different categories. We're going to be focusing our attention on integrating powers of the sine and cosine. Then we'll do the tangent and the secant. And then we'll be looking at the so-called reduction formulas where we're using trig identities to simplify the integrals that we're working on. Now, before we do that, I've got some reviewing for us. Let's begin by reviewing the so-called double angle and reduction formulas. So we start out, and this is something you might have run across before, maybe not. It turns out the sine of x plus y equals the sine of x times the cosine of y plus the cosine of x times the sine of y. And this will be the starting point for the so-called double angle formulas that we will need as we go along. Now, what we're going to do here is assume that x and y are the same value. We'll call that theta. Theta is usually used to represent degrees. So then algebraically, if theta is replacing x and y, what you've actually got here is the sine of 2 theta. And by the way, this is the origin of the name double angles. Okay, in other words, it's the sine of 2 theta. So we call that a double angle. And algebraically, based on what we just saw here, if you replace the x's and y's with thetas, this is what you'll end up with. Okay, so in other words, sine theta, cosine theta plus cosine theta plus times sine theta. And of course, what you've actually got here, if you can rearrange this one algebraically, you can rewrite that one as sine theta times cosine theta. So it's easier to see that you have this, the same thing added together. So this is our final result. We said that the double angle formula for the sine is, and then that is the formula, sine 2 theta equals 2 sine theta cosine theta. And again, the reason why this matters so much is because it may help us simplify some of the integrals that we're working on. And of course, you know that these can get very messy. So anytime we have the opportunity to simplify the problem that we're working on, we certainly will want to take advantage of it. And in trigonometry in particular, there's a lot of different formulas. There's a lot of different identities that we can use to help us simplify the problems that we're working on. Now, there's a comparable formula for this cosine as well. So this is the formula for adding up the cosine of x and y. You can see that the cosine of x times the cosine of y minus the sine of y times the sine of x times the sine of y. And once again, let's assume that both x and y are the same angle theta. So if you replace all the x's and y's, you'll have cosine 2 theta equals cosine squared theta minus sine squared theta. All right, so again, the double angle formula for the cosine is the cosine of 2 theta equals cosine squared theta minus sine squared theta. So probably what will end up happening is if you have an integral that is actually in the form cosine squared theta minus sine squared theta, one way you might potentially simplify it is simply to replace all of that with a cosine of 2 theta. And then you'll see in a bit that u substitution will probably probably be simpler that way. In fact, we'll see that a lot of these trig integrals can be solved with U substitution, but in many cases, we can really only do it after replacing a messy expression with a simpler expression. And in fact, the strategies in many of these cases will be to do exactly that. Figure out a simpler form for the problem that you're working on, and then at the end, use U substitution. Now, here's some identities that you might have forgotten about. These are all consequences of the Pythagorean theorem, by the way. So they're often called Pythagorean identities. So you can see the first one, sine squared theta plus cosine squared theta equals 1. And then we have algebraically, the cosine squared theta must equal 1 minus sine squared theta. And then algebraically, we could also say that the sine squared theta equals 1 minus cosine squared theta. Now, by the way, there are other Pythagorean identities that we'll encounter, but we don't need them just yet. All right, now, the double angle formula for cosines actually has two equivalent versions. We may end up needing one or the other, again, to simplify a problem that we're working on. So you recall from a few minutes ago that we discovered that the cosine of 2 theta equals cosine squared theta minus sine squared theta. But we also know that based on the Pythagorean identities, cosine squared theta can be rewritten as 1 minus sine squared theta. So we're going to do exactly that right now. Okay, so the Pythagorean identity, let me remind you right here, equals 1. So that means this can be rewritten as 1 minus sine squared theta. And so if you do that, you'll see that the entire expression is all in terms of sines. So the cosine squared theta is equivalent to 1 minus 2 sine squared theta. It may not seem like it, but this may be able to help us when we work on trig integrals. Now, there's another equivalent version of this. What we can do instead is, again, starting with our same Pythagorean identity, what we can do is say, well, if that's the case, sine squared theta equals 1 minus cosine squared theta. And that can get substituted in here. So we've got cosine squared theta minus 1 minus cosine squared theta, or we can rewrite that as negative 1 plus 2 cosine squared theta, or 2 cosine squared theta minus 1. Minus 1. Okay, so again, you have to take it as a given that this may come in handy, and it will. It definitely will. So far, we derived the double angle formula for the sine, which, by the way, it only has one useful version, the one we saw here. We're not going to be able to rewrite it in any meaningful way. There don't exist any other identities that we can use to change the way this is written. But it's simple enough. It's fine the way it is. It's this one, though, the cosine, because it involves a square term, 2 square terms actually, that we may be tempted to simplify it. And again, thanks to the Pythagorean identity, there's actually 2 different ways we can rearrange this algebraically. And I think down here somewhere I've got a little table, yeah, and to keep track of all this. It might seem a little bit overwhelming, so I just wanted you to see that here we've got the sine of 2 theta, And we got the two equivalent cosine formulas. And you can use the one that makes the most sense, depending on what type of problem you have. And then we also have something equivalent for the tangent. Now, here's another identity that you may not have run across. It's possible you've seen this before, but it turns out that the sum of two different tangents is equal to the tangent of x plus the tangent of y, all over 1 minus the tangent of x times the tangent of y. So once again, to derive a double angle formula, we will assume that x and y are both equal to theta. And so this is what we end up with. Tan x plus y is tangent theta plus theta. So ultimately, this tells me that the tangent of 2 theta can be written as 2 tangent theta over 1 minus tangent theta squared. Okay, now, as it turns out, that's as simple as this is going to get. So therefore, we have all of our double angle formulas. You notice that only cosine has more than one version. So these are the ones we may encounter. And we'll hang on to these until we need them. But it's important to remember this. In other words, if you didn't know these formulas existed, some of the problems that we're going to do, you would not be able to do them. It would be that simple. We really do need to know these or be familiar with them. Now, we have these other formulas called reduction formulas. And so the purpose of these is to take our double angle formulas, which we just learned, to simplify trig expressions. So here's an example. Now the sine squared of theta, what we're basically doing, by the way, is we're going to one at a time take these two equivalent expressions, the cosine of 2 theta. So the first version, 1 minus 2 sine squared theta, is here. So algebraically, we're just going to rewrite this as, oh, that's all it is. So in other words, what this is saying is that the cosine formula implies that the sine squared of theta equals 1 minus cosine 2 theta over 2. And you'll find that with a lot of the trig integrals that we'll be looking at, if you have a squared sign in there, it may be easier to replace it with 1 minus cosine 2 theta over 2. Among other reasons, because it makes it easier to use U substitution. It's not necessary, but it might be your easiest way of solving the problem that you're working on. What about this one? Now, this is the second equivalent cosine double angle formula, 2 cosine squared theta minus 1. And what can we do with this one? We can rearrange it algebraically and solve for cosine squared theta equals 1 plus cosine 2 theta over 2. By the way, once again, I do have a nice little chart here so you can keep track of all this stuff. What's missing here is the derivation. Okay, this is just a summary. So the derivations are here. And of course, as I noted, these are coming from the double angle formulas, which we derived from up here. So really, all of these results are just coming from these two formulas for the sum, the sine of x plus y, cosine of x plus y, and that one Pythagorean identity, sine squared theta plus cosine squared theta equals 1. With those three in hand, we can derive all of these results. All right, and then what about tangents? Now, here's where it gets really interesting. The tangent of theta, or any angle, is equal to the sine of the cosine of that same angle. Okay, that is how it is defined, which implies that tangent squared of theta is sine squared theta over cosine squared theta. Okay. So this is just the definition of tangent. And in fact, while we're talking about this, you might as well, we can review quickly that secant is 1 over the cosine. Cosecant is 1 over the sine. And cotangent is 1 over the tangent. Okay, just in case you've started to forget some of these definitions. So what does this get us, though? Well, you can probably guess. I mean, if you go back to this chart, we're going to find a way to simplify the tangent formula based on the fact that we have a squared sine and a squared cosine. So the clever way we do this is to note, well, we're going to use both of them, actually. Remember just a minute ago, we showed that the sine squared of theta is equivalent to 1 minus cosine 2 theta over 2. And the cosine of squared of theta is 1 plus. And both of these ultimately came from the double angle formulas. Okay, so these are just an algebraic rearrangement. So that means we can just take the ratio of those two expressions, and there we go. And that's our final result. The tangent squared of theta is 1 minus the cosine of 2 theta over 1 plus the cosine of 2 theta. So now our definitions are complete. We have all three of them right here in one convenient place. Now, you're not going to be asked to derive any of these, but when you're doing problems and you run into a squared sine or a squared cosine or a squared tangent, your strategy may involve replacing it with one of these. That's why they're called reduction formulas. The purpose is to reduce the complexity of the integral that you are actually working on. Now, here, I threw these in here because we're going to need these, just in case you're starting to forget. The derivative of sine x is cosine x. The derivative of cosine x is negative sine x. And that implies that the integral of sine x dx must be the negative cosine x plus c, and the integral of cosine x dx must be the sine of x plus c. So don't forget about these. Okay, you'll need them quite frequently. All right, so all of that is just background. Okay, so again, let's just quickly remember what we just did. We've got three basic techniques we'll be looking at in this section. The first section, we'll look at powers of sine and cosine. Then we'll turn our attention to tangents and secants. And then we'll be looking at the so-called reduction formulas again. So here we went through and derived the double angles. And they're summarized right here, keeping in mind that there's two of them available for the cosine. And then we also derived the reduction formulas. And then we had a quick review of the derivative and integrals of sine and cosine. There's more. If you go to your book, you'll see that every one of these is in the charts at the end of the book. And I know we've looked at these before, but hold on 1 second. So, table of integrals, yeah, they're all here. You can see them, in case you forgot. All right, now, here's where we're going to start. We're going to start, now, if you notice, cosine has an exponent of j, as does the sine in the second case. So, like I said before, many of these cases, what we're trying to do is use u substitution, but we want to have the expression here in the integral as simple as possible. And that's when all the substitution starts taking place. So also, what I wanted to do here is list all three of the Pythagorean identities, just in case we need them. Now, this is the one we've been using, but it turns out that if you divide across by the correct term, both of these two are implied by the first one. Like, for example, I don't know, maybe I'll just show you one of them just to show what I mean, just for the fun of it. So we know already that this is true. What if I were to divide both sides of this expression by the sine squared of x? Oh, I think I have goofed here. I think I was supposed to divide by cosine. Hold on one second. Okay, now this term is the tangent. This is just one. And as I mentioned a minute ago, cosine and secant are inverses of each other. So that's where this one comes from, the second one. The first one, you could derive it if you were willing to draw the triangle and set it up correctly. I think we'll save that for another time. But once that's been established, sine squared x plus cosine squared x equals 1. The next two are simply algebraic rearrangements of the first one. So then if you were to take this and divide by the sine squared, you have 1. Now, this is the inverse of the tangent, which is the cotangent. And then 1 over the sine is the cosecant. And if you look at the list, you'll see that that's exactly right. Cotangent squared x plus 1 equals cosecant squared of x. Okay, great. All right, I just thought you'd find that interesting. Now, we can have our first case. So what they're saying here is that as long as you have a situation where the cosine is raised to some power and the sine is not, then we can simply use substitution. No problems. It's easy. So let's try this one as an example. The integral of cosine cubed x sine x dx. So the question becomes, what do you do about the u? All right, so let's say that we let u be cosine x. Then du would be, as we saw before, let's go back and look at that chart, the derivative of the cosine okay, where is it? There we go. Derivative of the cosine, as you can see, is the negative sign. So that would be negative sine x dx. So what do we actually have here? Well, first we have to supply the negative ourselves. And so we've got u cubed, and this is du. And so that's going to leave us with negative cosine to the fourth of x over 4 plus c. It's very straightforward. And you can see that no matter what the exponent is on the cosine, it'll be very straightforward. Like if it was a 5, for example, we'd end up with cosine to the 6th power over 6. So this is the simplest case that we're going to run into, as you can imagine. Now, here's an interesting case. What if we have this? Now, the difference here is that the sign is not raised to the first power. It's raised to some arbitrary power k, and we're assuming that k is odd. So it could still be 1, but it could be 3, it could be 5, it could be 7. Then we're going to need this Pythagorean identity to help simplify results. Here's an example. So here we have cosine squared x, sine cubed x, dx. All right, beautiful. So this is indeed odd. So we're all set. This is our Pythagorean identity, which implies that sine squared x is 1 minus cosine squared x. So basically what we're going to do, since we don't have sine squared x, we basically have to provide it ourselves. But how do we do that? Let's find out. Our clever strategy is to say, well, we don't have an x squared, a sine squared rather, but we need one. So what can we do? Okay, so I'm going to put those up there so we don't forget. And so the strategy is to say, all right, why don't we rewrite this as actually, there's not enough space there. Hold on. Now, of course, that's the same thing. But now you see what we can do. Now, first, let's make the substitution. Now, it's starting to look like maybe we're making it unnecessarily complicated. Oh, well, that's not good. But you'd be surprised. Okay. So let's jump ahead here and see how that could work. All right, so this is where we left off. Cosine squared x, sine x, 1 minus cosine squared x dx. And so what we're going to do is choose cosine x for u, which, as we saw earlier, means that du is negative sine x dx. We don't have the negative. Oh, by the way, this is getting moved over here. We don't need to have the negative, but we'll provide it here. So what exactly does that leave us with? Oh. So in other words, if u is cosine x, u squared is cosine squared x. Now, we can just do a little algebra now, and all of a sudden, it's not going to be that big of a deal. And of course, we chose u to be cosine x. And I'm also distributing the negatives. Oh, well, that wasn't so terrible. Okay, but the thing is, when you first encounter one of these, the last thing in your mind is what can I substitute? Um, you really just have to get a lot of practice with these. The idea of turning sine cubed x into sine times sine squared, it would never occur to most people because it seems like you're making it more complicated, and technically you are. But what it does is it lets you start taking advantage of some of these identities that we've derived. And ultimately, remember what we're trying to do is use substitution. But in order for that to happen, like the way it sits right here on the top, we can't use substitution directly. We don't have the correct du in here, and we can't provide it. So this is a clever way of getting around that problem. So now, all of these cases that we're going to be looking at in this section requires similar types of strategies. It depends on what the exponents are for the x, the cosine and the sine. All right. Now, here's an interesting one. Now, we saw that based on our double angle formulas, we have a little chart up here. Let me go revisit it with you. This one. The so-called reduction formulas are derived from the double angle formulas. So let's say we had something like this. Okay, here it is. I just repeated it here. What if we have this case? Well, we're in pretty good shape here. Now, you might say, well, why don't we just do it directly? But no, it's easier this way. We're just going to replace sine squared x with what you're seeing here. Now, then we need a little algebra. We'll move this 1/2 outside. Inside the integral, we have 1 minus cosine 2x. We'll break it up into two pieces. 1/2 of integral dx minus 1/2 integral cosine 2x dx. This one can be solved with u substitution. The first one we don't have to worry about. It's easy. Okay. Clearly, this one is just going to wind up being 1/2 of x. It's this one we have to worry about. But it's not going to be too terribly complicated. So remember, it's negative 1/2 cosine 2x dx. So suppose we decide to let u be 2x. Then du is 2 dx. We don't have the 2, but we can provide it ourselves. We divide by half, and we multiply it. Oh, I just realized this should be x. And we multiply by 2. So that what we actually have here is negative a quarter sine u du. Now, earlier on, we saw a chart with trig integrals, just two of them. There it is. The integral of the cosine. Now, what I didn't show here is I could have also included this. Okay, and that's exactly what we're dealing with here. Anyway, so this is what it ends up being. So in other words, way back here, we have this expression, which we'll treat separately. The integral of 1/2 dx becomes 1/2 x. Then we're going to subtract this one, which ultimately turns out to be a quarter sine 2x. And so then we're going to subtract one from the other. And here's our final result. Okay, so it gets a little messy here because you've got an integral here with two components to it, one of which we can solve for with u substitution, the other doesn't really need it. So you basically have to treat them as two separate cases, but don't forget to bring them back together. And also don't lose track of these signs. Okay, so it's easy to do that. Okay, so just be aware that you've got multiple parts that you're managing at once and that you need to bring them together when you're done. And of course, if you're not sure if you've done this correctly, you can always confirm by taking the derivative and seeing if it matches up with the original problem. All right, now here's another interesting case. It turns out that there's yet another set of formulas that we can use to reduce or eliminate the number of times you have to deal with sine squared theta and cosine squared theta. So where did these come from? I mean, already we saw, well, actually, all right, let me go get it back for you. These are just slightly different. Here it is. Algebraic rearrangements of what we've already done. But I'm going to show you another way of deriving them besides the double angle formula. Yeah, you can see it's the same thing. I guess there's no reason why it doesn't really matter which way you write it. But both of these are being used in the book. So let me just go grab the other one so you can see how it stands up. So algebraically, they're the same thing. Now, it turns out that there's yet another set of identities involving sines and cosines, except this time they involve multiplication. And so what we're going to see is that if you use these rules, you can also derive these results. So in other words, you can use the double angle formulas You can also use these products. And so, for example, we can find this first one. Notice in the first row, we have the product of sine AX times the sine of BX, and this is the result. So let's just say that A and B are equal to each other so that we end up with the same angles. So what we're going to do is replace all the B's with A's. And so you can see this will be cosine 0. This is cosine 2AX. And this one could also be rewritten as sine squared AX. Okay. So then, and that's written on the next slide. The cosine of 0 is 1. So here's the final formula based on this one. But if A is equal to 1, then we have our final result. So yeah, whether you call it X or theta, it doesn't matter. It's the same thing. I like that. And then the second one can be derived in a similar way. From that last row, we've got the formula for what do you do when you're multiplying two cosines together. And the reason why these formulas are here is because they want you to see that the square formulas imply that A and B are equal to each other. If they're not, then this is what you do instead. Like, for example, you've got the cosine of 3x times the cosine of 4x. You can't use one of the square formulas because they're not equal to each other. So these are meant to be the most general possible expressions of what to do when you're multiplying sines and cosines. Anyway, so for cosines, this is the formula. Once again, we'll assume A equals B. Here we have 0. Here we have 2AX. This can be thought of as cosine squared of AX. And then, once again, the cosine of 0 is 1. And then if we assume that A equals 1, we're all set. All right. Any way you look at it. And of course, this one could be written if you want as 1/2. Or, there's different ways we can write this. It doesn't really matter. Okay, so finally, at long last, here's a case that we want to consider. And so, oh, by the way, in the beginning of this section, we mentioned that what we're looking for is this case. But that J or that K can actually be a 0. And that's exactly what happened here. So that means, and this is the 4. So therefore, we can use this approach. What are we going to do? Now, we don't have any formulas for sine the 4th. So what do we do about it? Here we go. Why don't we think of sine for the 4th power of sine x as the sine squared of x squared. All right, now, since we just got through showing that this is correct, if we square this, that means this is what we mean by sine to the 4th power of x. So we can multiply this out. We actually could use FOIL for this one. Let's do it. So F, O, I, and L. Here's F, a quarter. O, now this is a half times negative a half cosine 2x. So this is so the outer terms are negative a quarter cosine 2x. And the same thing is true with the inner terms. Negative a quarter cosine 2x. And then last is positive a quarter cosine squared 2x. All right, so what do we have? 1/2. Now, when we subtract a quarter and a quarter, we will have a half. All right. So once again, this expression that we just expanded is what we mean by the sine to the fourth power of 2x. I mean, sorry, of x. All right, so that's what we're seeing down here. So we just proved it by using FOIL. So we're going to bring that onto the next slide. Same thing. This is that result you just looked at. And now we're just going to break this up into pieces. Okay. Let's see. We have the integral of a quarter dx minus a half cosine 2x dx plus a quarter cosine squared 2x dx. Now this is where it can get very confusing. We've got three terms that have to be all integrated and then combined. So the first one is easy. Okay. What about this one? This one looks pretty straightforward. It looks like this one could be done with U integration or U substitution rather. So let's see. Now, if we do that though, we don't have the 2 that we need. So we will multiply by half and by 2. So we end up with a negative a quarter cosine 2x 2 dx. And so we got negative a quarter cosine u du. And that's equal to negative a quarter sine u. Let's see. Now remember, when we're doing it like this, we don't need to include the constant for every single term. We'll do that at the end. So this can be thought of simply as negative a quarter sine 2x. That's term number 2. All right, so just a quick refresher. Now we can think of this as term 1, term 2, term 3. We already know now terms 1 and 2. Here's term 1, x over 4. Term 2, negative 1/4 sine 2x. Number 3 is going to be a little bit more challenging. Or maybe not. Well, here's one of those cases, though, where we have an opportunity to replace cosine squared with simply a double angle formula. And that's exactly what we're going to do. So this ends up being the equivalent of 1/4 a half plus a half cosine. And that means we're going to have, if we're treating this as our theta, then we have 2 theta here. This becomes 4x. running out of space here. There we go. So we have to watch out for that. In other words, if we're going to use this identity, that means the cosine squared of 2x is what we're calling cosine squared theta. Therefore, based on this identity, this becomes a half it's a half cosine, not theta, but 2 theta. So if theta was 2x, that means 2 theta is 4x. Now it should be very straightforward to integrate it. All right, so this is the result up here. This is what we're going to call the third term. So we have 1/4 integral 1/2 dx. We're distributing this over the dx, integral of 1/2 cosine 4x dx. Now, oh, I see. I was wondering what this step was for. I just moved these outside. Okay. Now it looks like this will be easy. This one will use U substitution, where U will be 4x, du will be 4dx. We don't have it, do we? No, but we can supply it. So here, what I did here was I actually multiplied the 1/4 by these other constants. So we actually end up now with 1/8 dx plus 1/8 cosine 4x dx. The first term is just simply x over 8. This one, we're going to rewrite it as we're going to multiply by 4 and divide by 4. So in other words, 1/8 times a fourth is 1/32. So here's what we have. So that's just going to leave us with 1/32 sine x, sine u rather, which is 1/32 sine 4x. So, okay. Now, these two have to be combined. One 1/32 sine 4x. And don't forget that x over 8. So all of this is what we're calling the third term. So now we have to go back and gather up all the terms. And while it seems like we've been working this problem for about an hour, here is the final result. All three terms were combined, and this is what we end up with. Yeah, I know. Oh my God. So that's why I said, if, in a case like this, you've got to find some way of not losing any information, because we had to do 3 integrals, and one of them was done with parts, and that had to be split up into 2 more integrals. So we ultimately ended up with 4 integrals, and they all had to be combined. They had to be evaluated and then combined correctly. Wow. So now we're going to do this next example will be very straightforward. You can see the role now of this formula. And by the way, this is the only one we haven't used so far. If you look at this chart, it came from the book. These products, this is the one in the middle is the one we haven't used yet. the sine of ax times the cosine of bx. And what we're going to do, now, by the way, this time, a and b are not equal to each other. Think of this as a, and this is b. See. So the beauty of this formula is that it does not require them to be equal to each other. If it is, it will simplify it to something else like a double angle formula, but here they're not equal. So what does this give us? Well, so this will be 5 minus 3, and this will be 5 plus 3. So ultimately, we're going to end up with 1/2 sine 2x, 2 times x. Oops. I can't read that because I covered it up. Yeah, it is plus. All right. Plus 1/2 sine 8x. Okay, in other words, this and this are the same. All we need to do is integrate. And now we don't have to worry about the product. We have two relatively straightforward integrals that we can use and then combine them. Okay. So we end up here. And we integrate them each individually. And now each one by itself can be solved for with u substitution. Now here I'm providing the constant that I need, but don't have. In other words, here, u is 2x, du is 2x dx, 2 dx. And over here, u is 8x, du is 8 dx. All right. So let's focus on that first term. We're going to have 1/4 sine 2x times 2x. And here is our u substitution. And probably that would be easiest written as -1/4 cosine 2x. That would be the result of integrating this term. Now, the second term is this one involving the 8x. So again, you do not have the 8 that you need here for du. So we supply it ourselves. We multiply this 1/2 by 1/8, and here's the 8 that we need. So the integral of sine u is just simply negative cosine u. And so, or you could rewrite it as negative cosine 8x over 16. So remember, this is the second term, so we have to combine our two terms. And finally, this is where we are. Okay. So what's coming up next is our discussion about tangents and secants. And this will have its own set of shortcuts, properties, rules that we have to think about. So we'll save that one for next time. And we'll get some practice, and then we'll carry on from there. So the next section, by the way, after this is something called trig substitution, where you are able to take some of these concepts and use them to make other types of integrals simpler, not just straight ahead trig integrals. And so we'll be getting a lot of mileage out of trig functions in the next, this section and the next section, let's say. And then we'll go on to something completely different. But for a while, we'll continue to work on integration formulas before we start a completely new topic. All right, so I guess I'll just see you all next time.